All right, so now that we've talked a bit about the structure of the membrane and how it's formed, it's time for us to talk about two concepts that are going to be very important to us when we are talking about membranes. These are sort of general concepts of chemistry and biology, but they really come into play when we're talking about membranes, and those are diffusion and osmosis. You've probably heard about diffusion before. In fact, you've probably heard about both of these concepts before, but we're going to explain them in perhaps a little bit more detail than you have previously. Diffusion is the idea that things will naturally tend to move from areas of high concentration to areas of low concentration. So, for example, if you were to take a glass of water and you were to put a drop of food coloring in it, that food coloring starts out very highly concentrated where it hits the water. Now, if you just leave it there on its own, without any assistance, it will move from the area of high concentration to low concentration and spread out throughout the glass of water. This is diffusion. And it will continue moving from areas of high concentration to areas of low concentration until it is spread evenly throughout the entire container, the entire space through which it can move. There are many examples of diffusion that you probably encounter in your daily life, not just food coloring in water, but, for instance, smells in the air. If you were to spray, for instance, a bottle of cologne or perfume in the air in one place, you would detect it very quickly, and when it reached you, it would be relatively concentrated. It would be a very strong scent. Initially, somebody on the other side of the room would not be able to smell the scent right after you sprayed the perfume. Give it time, and the scent will diffuse throughout the entire room. And the person on the other side of the room will be able to smell it. However, by the time it gets to them, it will be less concentrated. As substances diffuse from high concentration to low concentration, their any individual concentration measurement, their total concentration, is going to decrease. All things diffuse. Anything that has the ability to move, I should say, diffuses. Things diffuse through liquids. Things diffuse through gases, and things diffuse through gels. Gels are a semi-solid media where you have liquid suspended in a matrix, like if you think of Jell-O or something like that. Things usually do not diffuse through solids. If I put a drop of food coloring on a desk, it will tend not to diffuse into the desk. However, things affect diffusion rates. So, for instance, consider our perfume example. What are the things that are going to cause the scent to reach the person on the other side of the room faster? Well, there are several factors that affect how fast things diffuse. First is temperature. We think of temperature as being like a property that things have. We say, oh, the air is 50 degrees. This piece of metal is 200 degrees. But when you get really down to a molecular chemical level, what temperature is the motion of particles. The more temperature something has, the hotter something is, the faster the particles that make it up are moving. If you have more temperature, more heat in your medium, that means that the particles are moving faster, and they will therefore diffuse faster. It's actually not just a speed of particles that goes into temperature, it's the kinetic energy of the particles. And kinetic energy is a factor of two things, both speed and molecular weight. Larger particles can have the same amount of energy while moving slower, right? So larger molecules are going to diffuse slower, because larger molecules at a given temperature are going to move slower. Think about diffusion, right? Diffusion always happens through something, whether it's a liquid or a gas, there are molecules there. Think about walking through a forest, right? Maybe you have a bunch of trees in our forest, right? So we've got a whole bunch of trees around here. And we have a person. I'll draw a little stick figure person right here. All right. Who's going to move quicker through this forest? Like a little kid, like this right here, or an adult who maybe is like a big guy with maybe like a big belly, kind of like me, right? Big guy, big belly, large person. Who's going to move faster through this forest? Well, the kid is, because they can just dodge in between these small breaks in the trees, whereas the big person is going to have to go through big gaps. They're going to have to squeeze through things. They're going to have to generally fit less well in the area. So the smaller you are, the easier a time you have moving through this medium, whether it's a liquid or a gas or a gel. So smaller molecules, lighter molecules, will tend to diffuse faster. Larger molecules diffuse slower. Next is the steepness of the concentration gradient, right? So if you have for instance, really, really, really concentrated area of blue, surrounded by, these gray here, then this diffusion is going to be more quick. Whereas if your blue is more integrated, right, less concentrated, in this case, the diffusion is still going to happen, but it's going to happen slower. Now, the next two apply specifically when you are diffusing across a membrane. Yeah, obviously, we're talking about diffusion and osmosis right after we talked about membranes, so these two things are going to be related. Diffusion happens everywhere, but in biology, we primarily care about diffusion when we're talking about how things diffuse across a membrane, right? So if things are diffusing across a membrane, the greater the membrane surface area, the greater the rate of diffusion. And that's simply because in order to diffuse across the membrane, whatever your substance is has to come into contact with the membrane. And a membrane with more surface area, let's say you have a membrane that looks like this, and then you have another membrane that just looks like this, and you look at the amount of our substance, our blue substance that's diffusing, that's in contact with the membrane, you just simply have more membrane surface area, and therefore a greater area of contact, and the blue is more likely to diffuse across a membrane with a larger surface area. Last, again, when we're talking about things diffusing across a membrane, has to do with the membrane permeability. Remember we said that cell membranes are, for instance, semi-permeable, selectively permeable. That means that they're going to let some things across and not others. And it's not exactly a digital state. It isn't either things can get across or they just can't get across. It's like there's a knob. That knob could be at 0, which is nothing gets across. Or the knob could be like at 10, which means that there's no impediments at all. But it could also be at like 5, which means that, there are fewer gates. Things can move across, but there's some impediment still imposed. Think of like you have a whole bunch of people that are in an auditorium, right? If there are no doors in that auditorium, they're all stuck in there. They're all basically going to die. They can't get out, right? If there are no walls at all, like it's an open amphitheater, then people can leave very, very quickly. They can leave basically as fast as they can walk. But those aren't the normal circumstances. Usually you're going to have walls, and those walls are going to have a certain number of doors in them, right? The more doors you have in your auditorium, the faster people will be able to move out of the area. The number of doors that you have is a representation of the amount of permeability of the membrane. So if you have more permeability, more doors, then things will diffuse across that membrane faster. Now, since we're talking about diffusion across a membrane, we have a special word for that. And that word is osmosis. Osmosis is specifically the diffusion of water across or through a selectively permeable membrane. And in biology, 90% of the time that we're talking about osmosis, actually probably more than that, 99% of the time that we're talking about osmosis, we're talking about osmosis across a biological plasma membrane, or a biological lipid, phospholipid membrane. You can have osmosis across like non-phospholipid membranes. You've probably seen like water purification systems that are called reverse osmosis systems. They use a different type of membrane filter. It's clearly not a cell-like based membrane filter. But when we're talking about biology and osmosis, we're almost always talking about a cell membrane. This is the diffusion of water. So the water is moving to the side where the water is more concentrated, to the side where the water is less concentrated. This membrane allows water to diffuse through, does not allow other things to diffuse through. Now, I know we said that biological membranes are they actually don't naturally allow water to move through. The phospholipid bilayer is a hydrophobic barrier and does not allow hydrophilic things to move through, and water is very definitely hydrophilic. But pretty much all biological membranes possess proteins called aquaporins. We talked about these a little bit, and you might guess from the name, aqua means water, porin means a pore or a hole. So basically, all biological membranes, or most biological membranes, have special holes that water can move through, but other things can't. Water can diffuse through phospholipid bilayers by itself, but it does so very slowly because it presents a fairly high impediment. The more aquaporins you have, the more doors you have in your amphitheater, and the faster water will diffuse osmosis across the membrane. Solute particles, specifically hydrophilic solute particles, I'm going to put hydrophilic solute particles cannot pass the membrane unless they also have a specific door, right? Each door only lets one thing across, and for our purposes right now, we're going to pretend that only water is getting across. In real life, it's a little bit more messy than that. For our purposes, we're going to pretend that water is the only thing that gets across. This is really super important for delivering IV fluids to patients. One of the things that is important, some of you may know, when you give fluids, let's say a patient comes in, they're severely dehydrated, and you need to give them fluids, you don't just give them pure water. If you give them pure water, you could actually end up killing them because it disturbs their osmotic balance. We'll talk about what that means in just a second. But this, when you have an osmotic imbalance, it can result in diarrhea, constipation, edema, the buildup of fluid in the tissues, as well as potentially hemolysis, the destruction or death of blood cells, and potentially other sorts of cell death as well. Let's see an example of osmosis. So in this picture, there are an equal number of particles on each side. There's 15 particles on each side. But on one side, all of the particles are water. And on the other side, we have a mixture of water and charged ions. This here in the middle, this is a selectively permeable membrane that will allow water across it, but not ions. So over the course of a time period, all of these things are going to come into contact with this barrier. If it's water, it will move across the barrier. If it's salt, it will not. Now I want you to think for a second and predict, based on the concentration of water on each side, which way the water will tend to flow, net, overall. Will you end up with more water on the left or more water on the right? Think about it for a second. Okay, well, now let's run the experiment and see. Right, so we have a net movement of particles, of water particles, from the left, or from the right to the left. Now note, before we had different amounts of water on each side, but we had the same number of particles. We had 15 particles on the left and 15 particles on the right. Now, where do we have more stuff? Is there more stuff on the left or more stuff on the right? Or is it still equal? If you go through and count them, you'll find that there's 20 things, 20 particles on the left and only 10 particles on the right. So we now have moved more things in to the left side overall. Now note that just because there was an overall movement from the right to the left, that doesn't mean that 5 waters moved from the right to the left. All the waters moved across the membrane. And in a real situation, all of the waters would move across many times. But the overall movement is from the right to the left. Now, when we think about membranes, most of the membranes that we're thinking about are in cells. So now instead of just having a left and a right, we're going to have a cell that's got an inside and an outside. All right? But other than that, it's pretty much the same experiment. We have 10 particles inside, and we have 10 particles outside. We have a higher concentration of salt particles inside, and a lower concentration of salt particles outside. Where does that mean we have a higher concentration of water? Think about it for a second. Well, if you count them up, you'll find that we have a higher concentration of water outside. Lower solute, lower ions, means more water. Inside, higher solute, higher ions, higher stuff that isn't water, means that you have less water. Now, let's take a look at what happens when osmosis takes place. Take a second, think about it, figure out where the water is going to move overall. All right, let's run the experiment. So you see what happened here. Everything hit the membrane. The waters crossed it. The salts bounced and remained where they were. We still have the same number of salts inside the cell, same number of salts outside the cell, but water has moved from outside the cell to inside the cell overall. It has osmosed inside the cell because it moved from high water concentration to low water concentration. The cell has a particular volume. It's round, like a balloon. What happens to a balloon if you put more stuff inside of it? The balloon gets bigger. Cells are no different. If you're moving stuff inside of the cell's got to get bigger to accommodate that. And so our cell got larger. This is a real force. Osmotic pressure is an actual pressure, just like air pressure or any other type of pressure. If you have a chamber, right? So let's say that you have a chamber that starts off with, all right, I'm going to draw the before condition here. All right. On one side, you have a 50% mixture of ions and water, and on the other side, you have pure water. And this membrane here allows water to pass, but nothing else. Where's the water more concentrated? It's more concentrated over here. Which direction is the water going to diffuse? The water is going to diffuse from high concentration to low concentration. Can these ions diffuse? No, because this membrane is selectively permeable. It allows water across, it doesn't allow anything else across. So if these two things started off with an equal volume, and then water moves from the right chamber to the left chamber, what happens? Well, over time, you will actually see water move, and you will see a different water level. That the water level on the right side of the chamber, or left side of the chamber, will rise, and the water level on the left side of the chamber will sink. Normally, to get water to rise from a level position, you have to pump it. It takes force to do that. Pressure to move water up. Here, you have pressure, but instead of basically hydrostatic pressure, which is what we usually think of as pressure, like you've got a pump that's pushing your water, we're doing osmotic pressure. Osmotic pressure pulls water from low solute concentration, that's low stuff, to areas of high stuff. Water will tend to move from areas where there's less solute, more water, to areas of more solute, less water. And that water can be used to do work, to move things. The process of reverse osmosis, which is used in some water purification devices, is just the opposite. You would actually be then putting a force, pushing force down on this side to force the water through, back through the chamber. Osmosis happens naturally. You do not have to put any energy in for osmosis to take place. Reverse osmosis requires energy. You have to push down on this left side to get the water to go back to the right. But you end up with pure water. Or purer water, at least. When we measure osmotic forces, we measure them in the form of what is called osmolarity. Osmolarity is a measure of tonicity, which we'll talk about in just a second. But basically, osmolarity is a measure of the difference in solute concentrations between two things separated by a permeable membrane. All the water cares about is how much not water stuff there is. Because what you really care about is how much water there is. Unfortunately, we can't measure water very easily. We can measure other things really easily. So like we don't have a way to measure and say, oh, this is 90% water. What we do have a way to do is measure salt and solutes. So we could say, oh, this is 10% glucose, or this is 10% sodium chloride. The other thing to keep in mind is that what matters is the number of particles, not necessarily the size of the particles, although there are some circumstances where that can matter. Osmolarity is measured in osmoles. In your chemistry class, you'll probably talk about moles a lot. For our purposes, what you need to know is that a mole is a measure of the number of particles. A mole is specifically 1 mole equals, basically 2.6 times 10 to the 23rd particles. It's a lot of particles. But when you figure that molecules are really, really small, you can pack a lot of them into a reasonable amount of space. 1 osmole is a difference of 1 mole of dissolved particles. And you have to take into account whether something ionizes when it dissolves. So for instance, glucose, if you take 1 mole of glucose and put it in water, a liter of water, 1 mole per liter, then you've got 1 mole of glucose in water. And it is therefore at a 1 osmolarity. Sodium chloride, what happens when you dissolve sodium chloride in water? Well, remember how we talked about how ions can dissolve and separate in water because the positive bits on the water are going to contact the negative bits on the ion, and the negative bits on the water are going to contact the positive bits on the cation, the positive ion. So in water, sodium chloride crystals in water dissolve into sodium ions and chloride ions. And since all we care about is the number of particles, and this thing has dissolved into 2 different particles that can now separate, for every mole of sodium chloride, you have a mole of sodium and a mole of chloride that dissociate. So you put in 1 mole of salt, and you now have 2 moles of particles. And all we care about is how many particles. So if you dissolve sodium chloride in water, a mole of sodium chloride per liter of water will give you 2 osmoles per liter of pressure, of osmolarity. Osmolarity is basically a measure of how much solute you have, how many particles of solute you have. And a difference in osmolarity means that water will osmose from one side to the other. Specifically, water will osmose from lower osmolarity to higher osmolarity. Body fluids contain many different things in them. They've got sodium, chloride, magnesium, calcium, potassium, phosphate, glucose, hormones, all of those things. And rather than knowing the concentration of each of them individually, we just talk about the osmolarity of body fluids. How much not water stuff is there in it versus how much water is there. Blood plasma, tissue fluid, intracellular fluid are all about 300 milliosmoles per liter. That is 0.3 moles of particles per liter of fluid. Osmolality, which you will sometimes see in chemistry, is the number of osmoles per kilogram of water. In normal conditions, 1 liter weighs a kilogram. So if you're in any sort of normal conditions, which we assume that living things usually are, because if you're in super abnormal conditions, then you tend to die. In physiology, osmolarity and osmolality are pretty much exactly the same thing. So if you see the 2 words, they're basically interchangeable as far as you're concerned. Tonicity is a relative value that basically compares the osmolarity of a cell, either a biological cell or some other container, to the osmolarity of the surrounding solution. And we measure the tonicity of the solution. A hypotonic solution, less tonic solution, means that there is less stuff in the solution than there is in the cell. Think about that. If there's less stuff in the solution, that means that there's more water in the solution. Which way is the water going to go? Is it going to go into the cell or out of the cell? Well, if we have a cell, and inside the cell you have 10% stuff and 90% water, and outside the cell you have 5% stuff and 95% water. Where's the water more concentrated? It's more concentrated outside. Which direction is the water going to go? The water is going to then go down its concentration gradient inside the cell. Hypo means less. Think of a hypodermic needle. Your dermis is your skin. A hypodermic needle goes under the skin. So hypo means less or underneath. A hypotonic solution has less stuff than the cell. Less stuff means more water. This will cause the cell to swell up. And like balloons, right? You know, you can put more air and more air and more air into a balloon. What's eventually going to happen if you keep blowing air into a balloon? It's going to pop. So if you take a cell and you put it in a hypotonic solution, it will swell and get bigger and bigger and bigger. And if this keeps happening, the cell can pop. Cells don't like that. They tend to die. A hypertonic solution is the opposite. Hyper means more. Think of like a hyperactive child. Does that mean that they're more active or less active? It means they're more active. Hypertonic means that the solution, the outside, right? So solution is outside. The outside has more stuff. Well, let's take a look at a hypertonic situation. Let's say that we have our cell, which still has 90% stuff, and let's say, well, so 90% water and 10% stuff, which could be anything, proteins, sugar, salt, whatever. But outside we have more stuff. Outside we have 20% stuff and 80% water. Which direction is the water going to go? Where's the water more concentrated? You got 90% inside, 80% outside. So the water is going to osmose out. What happens to the cell? Cell shrinks. So if you take a cell and put it in a hypertonic solution, there's more stuff, less water outside. Water leaves the cell, and the cell will tend to shrivel. The technical term for shriveling of a cell is crenation, or to crenate. It basically shrinks down and shrivels up. This is bad for the cell. It's not as bad as blowing up. Like, exploding will kill a cell really quickly. Crenating will kill a cell pretty slowly. Your cells can afford to lose water more than they can afford to take it in. But eventually it will kill the cell because the cell's now lacking water and it'll eventually die of thirst. An isotonic solution is a solution where you have the same amount of stuff inside and outside the cell. So let's take a look at an isotonic solution right here. Let's say we have a cell that has 90% stuff and 90% water and 10% stuff. And then outside you have 90% water and 10% stuff. Which way is water going to flow? Well, we would say that overall there's no net change in volume, but it should be pointed out that water will still flow out and water will still flow in. Oops, sorry. Water will still flow out and water will still flow in, but it'll happen at the same rate. So the water is constantly going to be flowing in and out and in and out and in and out, but you have just as much water flow in as you do water flow out. When you give fluids to a patient, it's important that you give isotonic fluids. If you give a hypotonic solution, you're going to cause water to flow into their cells. That could hurt their cells, eventually killing them. If you put a hypertonic solution into a patient, it will cause fluid to actually flow out of their cells. They will actually lose water. Even though you are putting fluids into them, they will become dehydrated. You may have heard that if you're ever trapped on a desert island, and you don't have any water, should you drink the seawater, the ocean water? No. Why? It's salt water. It is hypertonic to you. You can drink the seawater, but it will actually end up pulling water out of your body, and you will die of thirst faster than you would if you weren't drinking anything. Now, here's another important thing to keep in mind. Does it matter what the stuff is? And the short answer is no. The long answer is yes. No, it doesn't matter for tonicity purposes. And in fact, when you are putting fluids into a patient, you usually use 0.9% sodium chloride, because 0.9% sodium chloride has the same tonicity as blood cells. It's an isotonic solution for blood cells. And that means that it won't pull any water out, it won't force any water in. Now, you do actually need to care about it over time, because, if you give somebody a lot of sodium of 0.9% saline, well, blood is the same tonicity, but it's made of different stuff. It's not pure salt. It's got sugars and proteins and other things like that in it. So you do need to worry about the fact that you've added like a bunch of sodium to the patient, and they may end up with if you had to give them a lot of fluids, they may end up being hypernatremic, which means that they have too much salt in their body. But for the purposes of tonicity, it doesn't matter what the stuff is. So we just use 0.9% saline because saline is cheap and really easy to measure. Very easy to sterilize as well. It's important to sterilize fluids when you put them into a patient. So here's a question for you. These cells, these are all three blood cells, and one of them is in a hypertonic or hypotonic solution, one is in a hypertonic solution, and one is in an isotonic solution. I want you to take a few minutes and label them, or at least think about what solution each of them would be in. Go ahead and pause the video now and do that. All right, so let's start off with the easy one, right? Isotonic solution. An isotonic solution, you should have no net flow of water, right? You don't have more water flowing in, you don't have more water flowing out, so the cell should look normal. Which of these looks like a normal blood cell? This one does, so this is iso. What happens if you put it in a hypotonic solution? Hypotonic means less stuff in the solution. Less stuff means more water. If you have more water outside of the cell, water flows inside the cell, blowing the cell up. So which one of these looks like a balloon that's been blown up? This one. So this is hypo. What about a hypertonic solution? Well, we've only got one left, but let's actually think about it. Hypertonic solution means that it's got more stuff. Hyper, more, tonic, stuff. More stuff means less water. If you have less water outside the cell than inside the cell, water flows from inside to outside, and what happens to your cell? It shrinks and crenellates. So this is hyper. And you can see the crenellations here from it shrinking. All right, next time, so the important take-home points from this are you need to know what diffusion is and understand the concept that things diffuse naturally from high concentration to low concentration. You need to know what osmosis is, that it is diffusion across a selectively permeable membrane of water. You need to know what a hypotonic, hypertonic, and isotonic solution is, and what effect that will have on a cell that is inside of them. And you need to know what osmolarity or osmolality, whichever term, is. They're basically the same thing. But if I give you a question that says, a cell exists, a cell has an osmolarity of 300 osmoles per liter, and it is in a solution that is 150 osmoles per liter, what will happen to the cell? You need to know if it remains the same, if it crenellates, or if it blows up. In this case, lower osmolarity outside the cell means that there's more water outside the cell. Water is going to move inside the cell, and it's going to blow up. Those are the types of problems that you need to be able to solve from this section.